We now want to look at combining circuit elements, primarily resistors at this point. We're going to combine resistors in series and parallel. So recall that for a resistor having a current I and a voltage V with this designated passive sign convention, we have Ohm's law, V equals R times I, or I is equal to G times V, where G is conductivity and is equal to 1 over the resistance. So when resistors are placed in series, it's pretty straightforward that the effective resistance of the two is simply the sum of the two resistors. Right? If we look at this voltage here, that where I've labeled this voltage as spanning really those two, a branch that is composed of two resistors together, we would have V of R1 plus V of R2. Right? And so now all we have to do is replace that with R1 times I plus R2 times I, and now we have R1 plus R2 combined times I, and we can say V, the total V divided by I, is equal to R1 plus R2, which is also equal to the effective series resistance. So we show that it's the sum of the two. Now when we put resistors in parallel, it turns out, and you can verify this, that it is easiest to add their conductivities. Just like we add resistances when they're in series, we add conductivities when they're in parallel. And the reason that that makes intuitive sense is that when you put two elements in parallel, you're providing multiple paths for the current to travel. And so regardless of the conductivity, if you put two in parallel, you have increased the conductivity relative to either one of them. And so just like when you put resistors in series, regardless of the resistances, you are increasing the overall resistance, you are diminishing the current flow for a given voltage. So we have the dual going on here with parallel resistors. So the overall resistance, or the net resistance, GP for parallel, is equal to G1 plus G2. If you had a third resistor, it'd be G3 and so forth. If these were designated as, say 10 ohms and 5 ohms, then what we would have, say ohms instead of conductivity, then we'd say GP is equal to 1 over 10 ohms plus 1 over 5 ohms, and the parallel resistance then is the reciprocal of that, which is 1 over 10 plus 1 over 5. We can do a little algebra on that and multiply the top and bottom by 10 and 5, and we have that 5, we have the final result that 5 times 10 over 5 plus 10. And this is this parallel resistor formula down here. The parallel resistance due to two resistors placed in parallel is R1 times R2 over R1 plus R2. The simpler formula to remember is that the conductivity of the two resistors is G1 plus G2. Now if we have multiple resistors, like say 3 of them, instead in that case we would write their resistances are equal to 1 over the sum of their conductivities. Okay, and we see that in this formula here or here. The symbol, the double parallel line, is treated as an operator. So when we write R1 double vertical line R2, what we're really saying, R1 is equal to R2, so we'd say RP is equal to R1 parallel line R2, and that is equivalent to either one of these formulas here. Here's a quick example. We want to know what is the power absorbed by this 1 ohm resistor. So what we really need to know is actually the current that flows through it. So if we find I, then we can do I squared times 1 ohm. To get I, we want to collapse all of these resistors in this loop down to one single equivalent resistor, Req, and then we'll combine our two voltage sources as 150 volts minus 30 volts, or 120. So that's how we can get our I. So we simply need to combine our resistors. So walking around this loop, we start up here, and we see we have a 2 ohm, and then we go a little further and we see that we have a 10 ohm and a 40 ohm that are actually connected in parallel. So here's that parallel operator. That's in series with the next two elements, the 15 and the 60 ohm, which are parallel to each other. So we have plus 15 in parallel with 60. Then all of that is in series with 3, and lastly in series with the 1 ohm at the far right.